Hello, good morning, good afternoon, and good evening to everyone who's tuning in. Hope you're doing well and staying safe. On behalf of Petro Arab Oil and Gas Academy, SPE Egypt section, Arab Garo, I'd like to welcome you all for our today's session in Introduction to Cased Hole Logging. I am Mayar Tariq, senior year gas and petrochemical engineer student, Alexandria University, and I'll be your moderator today. I'd like to remind you to drop your questions in the Q&A section below and to make sure that the chat box is professional and ethical. And finally, please make sure to join the event's Google Classroom. Without further ado, let us give a warm welcome to the most renowned professor, Dr. Moustafa Oraby. Dr. Moustafa Oraby has a 25 years experience in petroleum industry. He holds a PhD degree from North Carolina State University, the United States, and a master and bachelor degrees from Alexandria University. Dr. Moustafa Oraby has joined Alexandria University in his early career as an assistant lecturer till he obtained his master's degree. Dr. Moustafa also used to teach at community colleges in the United States. In the industry, Dr. Oraby held many positions in all aspects of petroleum industry and lived in many countries around the globe. Thank you so much, Dr. Moustafa, for coming today, and the mic is yours.
Thank you, Mayar, for the nice introduction and the presentation. As Mayar said, good morning, good afternoon, good evening, everybody, wherever you are. Today we'll talk about a different subject. You probably did not study this in the undergraduate, but that subject is really a very important subject to all of us in the petroleum industry. Through the presentation and the course, you will see big differences between what we study in the formation evaluation compared to what we study or what we look for in the cased hole logging. Okay. So before actually we start anything about the cased hole logging, let's compare between the two environments, between the open hole logs and the cased hole logs. Open hole logs is whenever actually you drill a well, the well is still, the rig is still there, the well is still opened, there is no casing, there is no cementing, there is nothing but the hole that you drilled and the fluid that you drill with. So that's all what you face, drilling fluid, which is a mud, and the hole that, that you already drilled. So you'll see the drilling rig is there is no casing, the mud is filling the well bore, the fluids while you are logging is actually static or dynamic. It depends what are you doing. Are you doing this in LWD? Are you doing this in wild line? There is no perforations yet, so there's no fluid coming from your formation, no reservoir fluids, as we said. And also there is something else that we all face in this case, which is what we call the invaded reservoir. So the fluid is also invading. So in this case, you will not see anything coming from the reservoir itself, but the invasion comes from the mud itself, which invaded the reservoir. So that's the situation that we are used to see in open hole, which is not the case in cased hole. If you compare this to the cased hole, you see in the cased hole, you drilled the section, then you actually descended the casing. So this is the casing there, as you can see, it's right there. And the casing also you cemented after you set the casing into the well bore, you cemented, so you have the cement between the casing and the reservoir or the formation. Then actually you either keep a workover rig or you put the production. So you have the wellhead in there. Then you start actually possibly doing the perforation. So you have the perforation is there. So you perforated the reservoir. Then you see the fluids actually coming into the wellbore from your reservoir. So the reservoir now started to produce. When this happens, actually we have two situations. Either the fluids inside your wellbore are static, shut in, we call it shut in. It means you're not really producing the formation yet or the reservoir yet. So the fluids are in a static, there's no motion in there. Or the fluids are actually flowing, we call it dynamic. So in cased hole, we have two situations of our reservoir fluids. Either the flows are static when we shut down the well, we're not really producing. And everybody knows from the production logging you study in the undergraduate that you control this flowing or shut in from the wellhead by controlling the pressure of the well flowing in front of the perforations. So you actually can control if the fluid is flowing or the fluid is static. This is very important in cased hole, because in cased hole, we actually log a different situation. We can log while the fluid is flowing, and we can log while the well bore is in shut-in, means the fluid is static, is not really moving. Okay, the fluid that we deal with here in cased hole is not the drilling fluid, is not the mud, there is no mud. Okay, so what you're actually dealing with is the actual reservoir fluid. Then also, since this is the case, and since you started producing your reservoir, so there is no invasion. So we are not talking about invasion in this case. So many big differences between what we used to learn or what we used to see in the open hole condition versus what we see in the cased hole condition. Again, to compare apple to apple here, there is no casing in open hole, there is casing in the cased hole. There is no cementing in open hole, there is cementing in the cased hole. Okay? There is invasion in the open hole, there is no invasion in the cased hole. So big differences when you start really looking at what are we after, what are we looking for. So we understood from the open hole that we are looking for determination of the reservoir parameters. We need to find out how much porosity do we have, how much fluid saturation do we have, okay? So how much permeability do we have? You decide this in the open hole, okay? In the cased hole, these things are not gonna change. Porosity will not change, it will be the same. Permeability will not change, it will be the same. The one that's actually changing is the reservoir fluid. So now the reservoir fluids, because they just started producing, it's dynamic. So in this case, you will see changes in the fluids in your reservoir. Changes in the fluid of the reservoir means probably I started producing less hydrocarbon, because after a certain amount of time, you produce less hydrocarbon due to many things in the reservoir. Probably I started to see some gases coming out. I started to see some water coming out. I need to know where the gas is coming from, where the water is coming from, what happened to my reservoir, okay, what is the pressure in my reservoir. So all of these parameters we like to see, and these things actually goes on almost in a certain way of observing the performance of the well. So the cased hole function is much, much more than the open hole function. The open hole, we do it once. Cased hole, we do for the entire life of the well. We have to monitor this one. That's why sometimes we call it reservoir monitoring. We have to monitor the reservoir. What's really happening inside our reservoir, what are the changes in the reservoir fluid, what is the change in the reservoir, in the well bore itself. So there are so many aspects for the cased hole logging. Once we define this, then we have to go and look at what is cased hole. Okay, what is cased hole? I can actually divide this into 3 components. So just keep in mind, in cased hole, I divide all what I need to look for into 3 main components. Okay, the first component is inside the well bore. What's happening inside my well bore? What is the condition inside my well bore? So my well bore now is defined by the casing. What's inside my casing? Okay, what's really coming inside my well bore, because I don't see the reservoir in the well bore anymore. My reservoir is actually covered by the casing. So what's really happening inside my well bore? This is one aspect. Okay, the second one is what's happening between the well bore and the formation. What's happening in the casing? What's happening in the cementing? Is the casing in good condition? Is the cementing in good condition? So that's something else. So now we talk about the well bore itself, from the fluids contribution, the fluids status, what's really happening there. Then what's happening in the barrier between my well bore and my formation, which is the casing and the cementing. Also, what's happening inside my reservoir? What's happening to the fluids? How much hydrocarbon do I have left? Okay, where the water is coming from? If there is water, where is the oil is coming from? If there is oil, where the gas is coming from? If there is gas. So actually you divide it into three major components. Inside the wellbore component, between the wellbore and the formation, and then outside the wellbore, which is the reservoir itself. Okay. If you go and then do what are we doing for every one of these? What do we call them? Okay. So the inside the wellbore, we monitor the wellbore fluids. Between the wellbore and the formation, we monitor the casing and the cement. Okay. Outside the wellbore, we monitor the formation fluids. So we have three things that we need to look for: wellbore fluids, casing and cementing, and then the formation fluids. So that's what we really have. Again, when we look at this, then we call few things fluids. What do you really need to know about fluids? I need to know about the type of the fluids, the velocities of the fluid, the rate of the fluids are very important to us. So what are the fluids that we are producing? For example, if I am in a oil reservoir, I do not really need to see many or multiple gases or high gas rate that we see in our wellbore. I don't want to see any water coming out. So I need to look at what's happening in there, and if I can control the flow from my reservoir into my wellbore. The velocity, okay? The velocity of the fluids that's coming in. The flow rate of each one of these fluids is very, very critical in our evaluation of the performance of my well. So the cased hole is really well performance. And if you look at the whole number of wells, so it is a field performance. The second one is the condition of the cement and the casing. So I need to know, is the casing in good shape? Anything happened to my casing? Cement, what's really happening in the cement? Because sometimes if you are not really understanding the cement, when we reach that, we'll talk about something like a channel. Channel is really very dangerous in the life of the reservoir. We don't like to see any cement channeling between the casing and the formation. So these things are very, very important to monitor and make sure that the integrity of your well is in good condition. The third one is what's happening in my reservoir, the fluid, the three phases, the oil, the gas, and the water. Okay, what's really happening in there and what's the condition now? And we need to observe the condition of my reservoir every now and then, okay, every certain amount of time. I need to monitor what's really happening in the reservoir. So what do we call them in this case? The first one, we call it PLT, production logging. So whatever we actually look inside my reservoir, it's part of my production. So one part of the cased hole logging is the production logging. Production logging looks at what's inside my wellbore, okay, which is the velocity, the type of the fluids, the flow rate, all of these things we call it production logging. So the first part of the cased hole logging is the production logging. Second part of the cased hole logging is the casing and the cement inspection. So you have to inspect continuously the casing condition. You have to inspect continuously the cement condition. That's integrity of your reservoir. So the second part we call casing inspection and cement evaluation. This is also part of the cased hole logging. The third one is saturation behind casing. What is the water saturation currently now? What is the oil saturation currently now? What is the gas saturation now? So we need to know all of this. So if you look at any cased hole logging, sometimes people, and I can see that, even in the industry, people are mixing things together. They think that the cased hole logging is only the monitoring of the reservoir. That's not true. Cased hole logging, it has three components. The first one is the production logging. Second one is the casing and cement evaluation. Third one is the saturation behind casing. So if you keep this in your mind, that you have three different zones, every zone requires really a lot of attention, because this will control your productivity, your well performance, control even the integrity of your well and how the well is behaving, or if there's anything dangerous that you need to take care of, anything that may result in a blowout or whatever. You need to make sure that you're really in the good handle of the reservoir condition and on the well condition that you have. So the three components are production logging, cement and cement casing inspection and cement evaluation, then the saturation behind pipes. In every one of these webinars on the case logging, we will touch on some of these. Okay. Again, as just a word of advice for all of you guys, whoever is watching or learning any type of formation evaluation, regardless, it is open hole or cased hole, please make sure you understand the tools very well. I can see so many people actually, they started looking at logs and start to evaluate logs, and you go to the software and the try to upload data and do some very nice fancy plots, but unfortunately they don't understand. They don't understand what is the measurement itself and what are you looking for. Okay, if you don't understand the measurement, then you are in big trouble. You are not going to be able to evaluate, and you're not be able to really resolve what you see. It's important to understand what is this tool, or what are these tools? What is the basis of the measurement? You will be very surprised through these two meetings that we will have this Thursday and the next one, that the measurement of the cased hole logs are very, very simple tools. Okay, you will see this. I will go through each one of these tools a little bit on a slight way of looking at, but I will show you that the ideas are very simple. Once you understand the idea and how these people came up with these tools to define and measure all these parameters that we are looking for, you will be surprised. They are very simple ideas. Once you understand the idea and how we do the measurement, then it will be much easier to say, oh, if I see this, that this phenomenon means that. So because when you understand the tools and what it measures, it's easy to understand what the log is. And if there is anything that doesn't make sense to you, by understanding the tool and what the tool measures, you will understand that this is something real, or what does this thing that I see in the log means? Because there are so many things that you need to be careful when you do the cased hole logging. All right, so in this case, we will go for first one here. When I look at inside my wellbore, I can see so many things. Okay, here is my wellbore, and that's when I go for the production logging. I can see water coming in. I can see oil coming, gas coming in. I can see oil coming in. If you look at this example, it's an oil reservoir. It is an oil reservoir, and because once you started producing your reservoir, what's going to happen to the pressure of your reservoir? My pressure will go down, will decrease. The more I'm producing, the pressure will decrease. So it's the driving forces. The driving forces will decrease. Now, if you are not really perforating in the upper zone, let's assume that you have a gas cap on the top. If you have a gas cap on the top and you are not producing this gas cap, what will happen? The zone that you did not perforate still has its own pressure because you're not producing it. So in this case, the gas will expand and it will go through the perforation that you have, generating what we call gas coning. So the gas coning can come if you have a certain type of gas cap. Also, gas can come from the production that you have because if your pressure goes below the bubble point, you start seeing gases. Similarly, if you have an aquifer, you have a water zone at the bottom here. Here is a water zone at the bottom. Again, you started producing your reservoir. You have high pressure in this zone, and the high pressure will go and try to get into your perforation, and the water will come in. So you may end up producing gases from the top because of the gas cap that you have. You may have also produced water from the bottom because you have an aquifer that both the gas cap and the aquifer at a certain time, their pressure would be higher than your reservoir pressure. So in this case, they will actually go and try to get through the perforations that you have. So I need to know if this is really happening or not, and how I can control this. Can I go there and squeeze some of this perforation? I need to do something about it. So it's very, very important to monitor this type of fluids happening inside my wellbore. If you go to the second one, here is my casing, for example. I have a corrosion here in my casing. You can see that it's really very bad condition for my casing here. Here is one of the casing that pulled out, and you can see really very bad condition. And also you can see some holes in there, which we call pitting. So you can see some holes, you can see some corrosion. It can be even worse. It can be erosion in there. You can see it. Look at this, what's happening to your casing. I need to find this out. That can put my well in a very bad condition and can result in so many bad things that we, God forbid, that can be really a disaster in the field. So we need to know that. How can I identify this? How can I measure that? What are the tools that we use to do this? Okay. So this is really something that we need to monitor. Also, if you look at here, for example, there is a pitting or a pit happened inside my casing. So what happened if I have pit inside my casing and I don't have a good cement? Okay. So in this case, the fluid from the well bore will get into the zone between my casing and the formation. Okay, extra pressure will be building up. If I have a channel actually inside my casing, the fluid will get in and fill these channels. This is a big disaster that can result in a really big disasters in this well, and probably can result in something that we don't want it to happen. So monitoring this frequently in a certain period of time, we have to do this frequently to make sure that we are really controlling our wells well, and hence our field as well. At the same time, here again, here is our reservoir. Now we will talk about the reservoir fluid itself. How much do I have gas? How much do I have water? How much do I have percent-wise, saturation-wise? How much saturation do I have from oil? So we need to find the saturation currently and probably periodically every 6 months or every year, depends on your company. Some companies actually have a periodic every 6 months. We need to know what's really happening in our reservoirs. So that's the cased hole, and that's what we are looking for. And that's what we really need to monitor every time and every now and then in the life of our field. So let's start with that. From that definition of what is the cased hole, let's just start to see how can we do this. What are the tools that we use in this case? Okay. So let's just start with the first one, inside the well bore. Okay, so we'll start today inside the well bore and see how can we measure, how can we identify, how can you predict what's really happening inside my well bore, which we called previously PLT, or production logging tools. So the production logging tools will be the one, or production logging will be the one, is the first one to start with, to really monitor what's happening inside your well bore. So if anybody is talking about production logging, you know that they are monitoring what's inside the well bore. So important question to answer, we always say, is there any gases coming from the formation? That's a big question. That's a very important question, actually. In many situations, we don't want to see these gases coming out, okay? Sometimes the gas rate is very low and it causes some issues, just don't know even what to do with these gases. Okay, some of us go and flare these gases, and you know now nobody likes to flare things, okay? So it's very important to know, is there any gases coming out of the formation? Also, is there any water coming from the formation? This is very important two questions. And it's not just if there is any water coming in or any gas coming in, from where it's coming in. What are the perforations that's actually giving us or providing us with these gases? Or what are the perforations that are providing us with this water? Probably if I know the location, if there is a way to fix this, I need to go and fix it. So before you go and fix, I need to know where it's coming from. First of all, is there any of them? Second, where it's coming from. Okay. So the answer to the question, if yes, as I said, then where is it coming from? And is the gas cooling or is gas from the reservoir? I need to understand that very well. Similarly, if I have water and the answer is yes, you have water, then I have to say, where is it coming from? And also, is it coming from an aquifer, or is it coming from the low pressure, or something I need to deal with as far as the reservoir is concerned? So answering the two questions, yes, I can see gases coming from my production. I can see gases. I can see water is coming with my fluids. okay? But that's not the answer. Yes, I can see that from the wellhead. I can see from the fluid that's coming at me. But the question, the most important question is from where? Where is it coming from? Which perforation is providing these type of fluids? We'll look at some examples here to show you that some of the perforations will produce water, some of the perforations will produce gas, other perforations will produce oil. So we'll see some of these examples to show you how can we find this out. Okay, again, that's the same. I always use this actually to explain the gas cap and the water coning. And these are very bad things. When you see coning, that's not really something that we like to see. And we need to control this very well, okay? Okay, so let's start with the gas first. Where the gas is coming from and what are the reasons for the gas is coming from, okay? So what happens when the gas flows in the wellbore? We need to answer that question very clearly from the physical understanding of the gas itself. And also, once the gas come in, how can I detect it? How can I know the gas is flowing, okay? Because I need to know where it's coming from and also how to handle this. So what happens when the gas flows into the wellbore? Very interesting question. What happens is actually here is my well, and let's assume here are my perforation, and let's assume I have a gas cap there, okay? And I started producing my reservoir. So this is the gas cap on the top, here on the top of my perforation. So I actually did not perforate in the gas cap. I perforated in my oil zone. Okay, gas cap is above. Here is my oil zone. I perforated inside my oil zone. Okay, so this is my reservoir, which I'm producing from. But above me, there is a gas cap. Right? Through the time when you start producing, the pressure will decrease. Your reservoir pressure will decrease, but you are not producing the gas cap. Okay, so in this case, you're not producing the gas cap. The gas will expand and go inside your formation, and it will actually see these type of perforations. So the gas will come through these perforations, okay? And that's what we call the gas coning. So gas is coming from here. Here is low pressure. Here is high pressure. The gas will for sure expand, and we'll see that gas will coming through this type of perforation, and boom, it actually gets into your wellbore. So the gas is coming inside my wellbore. What will happen in this case? How can I detect this flow of gases? And how can I know it's coming from this zone, not from any other zone? Okay, so it's very, very important to know that. So what we do actually in this case to identify the zones that producing gases and where it's coming from. Okay, so when the gas is actually comes out, it expands. Okay, we know that gas expands. If you do this at home, you just get your perfume or something, you just press something. When you press the perfume head, what will happen? You actually lower the pressure and then the gas will expand. Or the perfume, which is a type of gas, it will expand. So the gas expands. Okay, so what when the gas expands? Well, when the gas expands, actually what happens is it loses temperature. It lowers the temperature of the surrounding. So the temperature of the surrounding decreases. Oh, so we now identified a phenomenon. We will talk about this phenomenon in a minute and why this is happening, because it's important to know why the temperature decreases. Okay, we know I don't want you guys as an engineer, don't ever memorize anything. Everything has a good reason. We need to understand the reasons behind it. Okay, so when the gas expands, temperature decreases. So the point is, if I need to find out if this zone has gas or not, what can I do? Very simple, measure the temperature. It's very simple. So if you need to know where the gas is coming from, it's a simple thing to do. Since the gas, when it comes in, it expands, and when it expands, it loses energy. When it loses energy, its temperature decreases, then it will cool down the zone that's coming from. So these perforations, if I actually measure the temperature in front of these two perforations, my temperature will read lower. So I need to actually build a tool that measures temperature. It's as simple as such. If I build a tool that measures temperature inside my wellbore, and while I am measuring the temperature across my wellbore, I found that the temperature is decreasing, I know this is where the gas is coming from. I know the gases are coming from the wellhead. I know that. I don't need anybody to tell me I need to go inside the well bore to find the gases coming. No, the gases are coming. I can see that in the wellhead. I'm producing them. But the question is from where? From where is more important than do I have it or not? From where? So I can deal with it somehow. Okay. So from where? Simply go and measure the temperature across your well bore. What will happen in this case? If your perforation or certain number of perforations that you have are producing gases, the temperature will be cooler. The temperature will drop. So that will be the thing that we actually find out where the gas is coming from. So the temperature goes down. Well, gases actually expands, and when it expands, it loses temperature. Now, it actually follows this. To understand this, we need to follow the Joule-Thomson rule. What the Joule-Thomson rule that we study in reservoir engineering? Well, it says any gases, when they expand, they cool down. Okay, that's good. But we need to know why this is happening. Okay, we don't want to take things, we are engineers, we don't take things as is. Why this is happening? Why this is happening is very critical. Actually, what happens is the cooling occurs because when the gases actually move, this means the gases are coming from the perforation. It comes out, so the molecules of the gas are separating. Okay, separating means they are actually take more space and it moves in a faster way. So the molecules of the gas moves faster. Okay, what does it mean when move faster? Velocity increases. What does it mean when the velocity increases? Energy increases. So the energy increased because energy is half mv squared if you took it classically. Energy is half mv squared. And if the velocity increases, energy increases. Where the molecule got the energy from? From the surrounding. So the molecules take the energy from the surrounding. So the surrounding has to cool down because it gave its energy to the molecule. So that's the whole idea. Gases were actually inside the formation are under pressure. When it leaves the formation and goes into the well bore, the pressure decreases. When the pressure decreases, gas will expand. When the gas expands, actually they gain velocity. When they gain velocity, this means that they are taking this energy out of the surrounding, so the surrounding cools down. So we now understand the phenomena of why the temperature decreases. So why the temperature decreases? Because of the expansion of the gas, the high velocity that the molecules of the gas are actually taking this energy from the surrounding, so the surrounding has to cool down. Okay, so the reason that the temperature decreases is because of the expansion of the gas. When we talk about hydrogen and helium, I don't want to go through this because it's our two exceptional gases. They are not really follow the same rule, but all other gases except the hydrogen and the helium, and thanks God we don't have them inside our well bore. So actually these things, all the gases now that we deal with inside our well bore will cool down if they come out of the perforation. Okay, so we understood the idea, we understood the signature of if there are any gases coming in or not. So in this case, what we need to do, we need to design a temperature log. So the whole thing is how to measure the temperature now. So we understood that the temperature cools down. Then to find out where the gas is coming from, go and measure the temperature across your well bore. When you see a drop of temperature, in this case, this is where the gas is coming from. Okay. Well, how to measure temperature? As I told you guys, most of these tools are very, very simple tools. Okay, understand the idea, then you will be very easy to interpret all these tools. Okay, so this is going to take you back to elementary school, and I'll show you exactly it's elementary school. In elementary school, actually, it told us what happens to the resistance when you heat it up. When you get a certain metal that has a resistance, and you started heating this metal, what will happen to the resistance? Well, the resistance will increase. Why is that? Actually, I used to see these things that comes out, even I got this even from the internet. It's a very interesting cartoon, okay, that shows what's really happening. Now, If you raise the temperature here, they're showing the electrons as these kind of funny things here. Okay, so these are the electrons. When they come into through the rod or the iron or whatever, they see an area that's very, very hot. So they cannot really move because it's really hot. Okay, so in this case, the electrons are not moving. So the electrons will slow down. So the slowing down electrons means there is no current coming in. There is no current coming in means the resistance is high. So the temperature, the higher the temperature, the higher the resistance. So this is very nice. When the temperature is high, the resistance is high. When the temperature cools down, the resistance goes down. So it's very simple. Just a very simple resistance. Make a tool with a very simple resistance and go and measure temperature with. Does the temperature gets higher or the temperature gets lower? If the temperature gets higher, this means the resistance of this wire will get higher. If there is a cooling down, then the resistance will get lower. So the higher the resistance, the lower the resistance will indicate, do I have higher temperature or lower temperature? The question is that really what we do in the case hole logging? Yes, that we do in the case hole logging. Is that the way that we discover where the gas is coming from? Yes, that's the way that we discover where the gas is coming from. It's a very simple idea. And as I said, if you really understand the ideas of the tools, it will be very interesting. They are all very simple ideas, but we need to understand what they measure. So in this case, we really understand how to interpret things, okay? So the whole thing is the resistance increases, okay, when the temperature increases, okay? Let's just go now and get some equations with it. Here how what's happening. Rho, or the resistivity, is rho initial times 1 plus alpha T. T is the temperature. Alpha is what we call the resistance coefficient or resistivity coefficient. That's every metal or everything that has resistance, it has certain coefficient as a function of temperature. For example, iron is different than steel, is different than nickel, is different than all these elements. So every element has a certain resistivity coefficient. So when the temperature increases, you know that the resistivity will increase. T is your temperature. Okay. So this is the simple equation that controls how the resistivity increases as a function of temperature. Okay. As you can see here is a straight line increase with a slope of alpha, which is the resistivity coefficient. So you go and choose a certain metal to use in your temperature log, and that's it. We don't want to go through all the details of what are the temperature or what are the resistivity they are using. That's not really important. What's important to us, we will see a change in temperature, and that change of temperature will indicate the existence of gas or not. Okay. All right. So this is the phenomena that we use for measuring temperature. Okay. So let's, in this case, just see what's going on. Here is a schematic of a tool. You can see this. This is a temperature sensitive resistor. So I have a resistor here, sensitive to temperature. It means that the coefficient is very high. So you choose a certain type of metal that has a really high sensitivity of temperature to make your tool more sensitive. Well, this you do. Do you really care about this as a user? No, you don't. But you really understand that. You understand they measure this, they do this, they make these tools out of a resistor that has sensitivity to temperature. Okay. So in this case, when the temperature increases, that resistance will increase, and it will indicate what is the increase of that temperature. Okay. With this understanding, let's just see an example. Here is an example coming from India, for example. Okay. It is a well. You can see this well. It has multiple perforation, and I use this well all the time because it has really a lot of perforated zones. We have 1, 2, 3, 4, and so on, and you end up at about 19 or so zones. So all these zones are perforated based on, well, this will produce hydrocarbon, this will produce whatever. So they actually, according to the open hole logs, they decided to go and perforate all these zones. Okay? Now, here is my gamma ray, okay, as you can see right there. Now, Now we ran the temperature law. Here is the temperature law. Before we go into how to evaluate the temperature law, let's just see something very important. You have multiple passes. That's something we do in every cased hole logging. We do multiple passes. Remember, in the open hole logs, we don't really do logging going down. Okay, that's not a normal procedure of logging. We always do logging pulling up. Okay, because we need to make sure that the stretch of the cable and stuff. In cased hole, since the environment is a little bit on control, we can actually do some corrections for the speed, the cable speed and stuff. So we can actually do logging down and logging up. So we do actually logging down and we do logging up. And we don't do this only once, we do it multiple times. So we have to do multiple passes, okay? Multiple passes we have, for example, in this well, we did 4 logging down. If you look at this, D1 means down 1, down pass 1, D2 down pass 2, D3 down pass 3, and so on. We have 4 of them logging down to actually acquire the data 4 times. And you look at all the data, you don't have to average, but you need to look at the consistency and how the repeatability, how these data are repeated. So we actually do logging down, we are logging down here, and also we do 4 logging up. So you go down and you go up, again you go down and you go up 4 times, okay? And you look at all these measurements. That's why you see multiple of stacked curves. These stacked curves are 8 of them. 4 of the measurements going down and 4 of the measurements going up. Okay, so you can see 4 going down and 4 going up. Now, to understand what's happening here in this temperature log, I can go from bottom up. For example, I can see a very nice decrease of temperature, but this not in any sudden way. This is actually a very nice behavior of temperature loss. The temperature will decrease in a linear way here. So there's not really nothing abnormal happening here. So there is no change of temperature here, sudden change of temperature. This is the gradient that we expect inside a certain well bore. So this is actually a normal gradient of change of temperature because temperature increases going down and decreases going up. So the temperature is decreasing in a very nice way. But we did not see this happening up here. It's not really going in the same linear decrease and it goes in that direction all the way up. No, we can see now big difference between what's happening down here and what's happening up there. I can see drop of temperature clearly, especially in this zone right here. I can see a very interesting drop. Now, if I look at the scale here, the scale is from 270 degrees Fahrenheit to 330 degrees Fahrenheit. So between these two actually is about 60 degrees. If I divide 60 degrees over this 10, then each one of these will have 60 degrees. If I look at what the drop here, it's about 2 of them, or maybe 1.5. It's about 12 degrees. So the drop in the temperature here is 12 degrees at this specific point. 12 degrees drop in temperature. If you see that very high drop in temperature, no question, gas is coming from this zone. No question asked. Gas is coming from this zone. I can see the drop of temperature, very high drop of temperature, 12 degrees at this one. So in this case, these perforations are producing gas, no question asked. So in this case, if we don't want to really need to produce this gas, or it depends if it's a gas well or just a gas cap, so we actually need to do something about it. So that temperature drop here. And if you actually work in cased hole, don't go for 1 degree or 1.5 degree or 2 degrees as a decision maker. No, they have to show something big. 5 degrees, 6 degrees, yes, until I can say, yeah, there is a drop. Plus or minus 1 degree or plus or minus 2 degrees, because also oil can do some tricks. Oil can also drop the temperature a little bit. It's not as dropping temperature as gases. And that's why we always say considerable means 5-6 degrees until I see, well, this is really coming out of gas. So we actually understood now that this drop is really big drop. 12 degrees drop, indicating that this one has gas production. So from the simple idea of measuring temperature, I can identify which perforation here is actually producing gas, okay? Which perforation is producing gas. There's some other tricks that we always do when we look at the the cased hole logging, but I just want to, in this webinar, just to touch base with you guys on what are the ideas and how can we predict, okay, something happening like what we see right there. So the drop in temperature indicated gas production from this type of perforations, okay? Then we come to the second one, water. Water is coming in. Where the water is coming from. So we understood the gas and we understood the idea of the gas. You'll be also very surprised that the idea of detecting water is much simpler even than the idea of detecting gas. We detected the gas by the simple temperature, and we understood that when the temperature actually, when the gas comes in, temperature cools down. You just go with measure temperature, and all what the tool is composed of is a resistor that really goes up and down by the change of temperature. So about the water, water is coming in. How can I identify water? Well, let's go back to middle school. Remember, the temperature was in primary school. Okay, let's just go to the middle school. What's really happening in we studied something called capacitor. Let me remind you what is the capacitor. Well, they told us in this elementary school that if you have two plates, every plate has an area A, for example, and the distance between the two plates is D. Now, if you leave air between the two plates, okay, nothing inside but air, and then you put a battery between the two plates, what will happen? That the positive charge from the positive side of the battery will go and live and stay on that plate, on the surface of that plate, and the negative charge will go and stay on the surface of that plate. So you will end up creating positive charges here and a negative charge there. And it's actually stored there. So the capacitor is the one that stores these type of charges. That's something that we studied in middle school. Then when we progressed into this and started to look at the circuits and how we measure the capacitor, we identify something called capacitance. Capacitance you identify by two different methods. Either by the charges that you actually accumulated over the surface, or by the design and the geometry of the capacitor. So you can actually calculate the capacitance by two different methods. Okay, by the charge that was accumulating over the surface of the capacitor, or by the geometry of the capacitor. Okay, so in this case, the deposited charge, we identify the capacitance as the deposited charge per unit voltage. So I have a charge here created by a certain volt. So the charge that I got over the plate of the capacitor per unit volt is actually what the capacitance is. So the capacitance is Q over V. Okay, so the charge over the voltage. That's good enough. Or by the dimension of the capacitor. Dimension means I have a capacitor with an area A and a distance D, and there is air in between. Okay, now in this case, I can actually calculate the capacitance as well. It's epsilon naught A over D. A is the area of the plate, D is the spacing between the plates, epsilon naught is what we call dielectric constant. It's actually related to the filling between the two plates. Okay, so this is the geometry that I have. I have plates that has certain area, between the two plates is a certain distance, and filling between the two plates with a certain material. I'm not having any material here, I'm just having air. So we call it epsilon naught, or the dielectric constant. So epsilon is a dielectric constant that prevents the charge from moving. So in this case, I can calculate the capacitor by Q over V, or the capacitor by the dimension of the capacitor. Okay, so that's a very simple thing that we studied. Probably when we studied this, we didn't understand what is this for and why you are studying this, until you see this is what we do to really evaluate, do I have water in my reservoir, in my wellbore or not? and I can identify where the water is coming from. Okay, so that's a very simple thing that you studied even in the middle school. All right. So don't get a little bit of oh, this is cased hole, so many tools, guys. We are engineers. Nothing will be hard if we understand what we see there. Okay? So in this case, what happens if the distance now between the two plates doesn't have air? Okay. Well, in this case, according to this equation, the capacitance will change. All right. So if the material is not really epsilon naught is the air. What about if I put something else, not the air? Well, area is the same, it's fixed. Distance is the same, it's fixed. The only thing that you change is whatever in between the two plates. Okay, if what in between the two places air, we calculate it as epsilon naught A over D. What if it's not really air? Well, let's just see what's happening. If these are my two plates here, and actually a fluid came in, oil or water. Now we really know where are we going through now. So we'll allow the fluid to get between the two plates. Okay, then the capacitor will change. Well, what if actually only water or only oil? What will happen? So the capacitor will change in a way. It will be epsilon naught epsilon R. Epsilon R is the dielectric constant of the material that lives inside the capacitor now. Okay, so you actually added the material to the capacitor. So multiply epsilon naught epsilon R, which with the epsilon R is the dielectric constant of the material that now exists between the two plates. All right. Epsilon naught is for the air and epsilon R is for the material. That's great. Well, now if you look at oil or water, what is epsilon R if it is oil? 2.2. What's the epsilon R if it is water? Is 80. Big difference between epsilon R of oil and epsilon R of water. Then, well, I can easily use it to identify water because my capacitor will read very high. Okay, my capacitor will read high capacitance. So the high capacitance will happen if water gets through the capacitor. Look at how people think. It's very interesting, very simple idea. But that's how we identify. This is what they call the capacitor log. You hear about the capacitor log probably if you are working now in the industry, hear the capacitor logs in the production logging, but you may not know what is the capacitor log. Why the capacitor will actually find out where the water is. So that's the reason. The dielectric constant, when the water comes in, the dielectric constant of the water is much higher than any other fluid. The electric constant of gases is very, very low. So water is actually 80 and oil is about 2.2. So that's the whole thing. Well, if this is actually my casing, now I'm not really drilling a formation. This is my casing straight line. This is my casing here. Now, if I put a capacitor, okay, two plates. Well, but the plate here, if I take it that shape, that geometry, is not going to fit my well bore. My well bore is cylindrical. Well, it doesn't matter. Then you do two cylinders. Instead of having two plates, make it two cylinders. Inside cylinder and outside cylinder. And allow the fluid to go between the two cylinders. Okay. So there's an inside cylinder and outside cylinder. And this area is empty here. Now, if the fluid comes in and fills the area in between, now we measure the capacitor. If the capacitor C reads very high, then if the capacitance reads very high, that's an indication of water. And if it is very low, that's an indication of non-water. Okay, I don't really care if it's oil or gas. Now I need to identify the water. So gases we use to identify the gases from the temperature log. So I don't have a problem with that. I don't really care of this, and I need to identify where the water is coming from. So when I see the capacitance increases, okay, so in this case, I really understand that the water is coming from this specific zone when the capacitor goes through it and the capacitance increase. Okay. All right. So identification of fluids, the capacitance is very, very easy for the water identification. Okay. That's really true. Here is a schematic of what the capacitor is all about. Here is the inner one, and here is the outer one. And the flows actually come between the in and the out, similar to what just the cartoon that we drew. Actually, people do even much more than this now, okay? With the same idea of the capacitor. I'm going to change the idea, but people actually think a little bit of more and more. Can I actually do this looking at the circumference of the well bore? The circumference, instead of having one measurement in the middle, can I go for the circumference? I can see exactly around me, okay? So yes, you can. So what they do? They actually create multiple capacitors. They call it multi-capacitor or multi-fingers. Multiple capacitors. And these capacitors are actually across the well bore diameter, across the casing, okay? Or inside the casing, making across the well bore diameter. Now you allow the fluids, okay? You can see that all of them are across a circular shape, okay? Now you allow the fluid to come in. So you can see if there is even bubbles of hydrocarbon coming with the water. So you can see that array of capacitors. So instead of using one single capacitor, because the idea is very simple. What's the point? The capacitor, to design a capacitor doesn't take that much. Huh? So the idea is very simple. So you actually allow the water to come in and you measure this through capacitors, right? Do I really have a tool like this? It's exactly there. Here's the tool. The tool is multi-fingers, okay? All of these end of the fingers here are capacitors. This capacitor, the tool opens inside the well bore and shrinks, so we can actually see the capacitors and the water and the water distribution, even across the cross-sectional. Sometimes you guys we talk about something called hold up. I don't want to go through the hold up now, but for the hold up, which you can see what's really happening across the cross-sectional part of your well bore, then the capacitor will be the easy way to go, and you can measure the distribution of fluid across the capacitors. So that's the real thing that we use. For example, this is an array capacitor. Let's go back to the same example that we did. Did we run the capacitor there? Yes, we ran the capacitor there. So we ran the capacitor, actually, first one, you can see very nice lines. Well, that doesn't really happen in our reservoirs. I mean, how can the well bore that really nice, very sharp? I can see difference here from there, very sharp difference. When you see something like this, you know this is what we call shut down or shut in. The well is shut in. Things are static, no movement. So that's why I remember when we started looking at the cased hole, we said we look at it in two different situations, a shut-in situation and a flowing situation. When you shut in the well, there is no movement. So you expect something very nice and tendy like this one. So you can see a transition, clear transition from the capacitor. Again, you can see 4 going down, 4 going up. We don't run every tool separate, and we run a stack of tools. So actually, these are stacked together, 4 down, 4 up. Here's also the capacitor, 4 down and 4 up. You can see clear transition here. So this one indicating water, and this one indicating hydrocarbon. I don't care what type of hydrocarbon. I'm after indicating where the water is coming from. So my capacitor will be where the water is coming from. If I need to see gas, I already did this by the temperature. That's why I combine the temperature log and the capacitor log. Temperature log will identify the perforation that produces gases, and the capacitor log will identify the one that will produce water. So identified what's producing gases and what's producing water. And you can see clearly here a very sharp transition. That's in the shut-in. Okay. What will happen if I flew the well? If I let the well actually flowing, when I get the well flowing, okay, here is the well flowing. Now I can see a change in the level of the water. So I did it in shut-in and I did it in flowing. People will say, why are you doing this? Why you're doing this in shut-in and you're doing this in flow? Well, I really understood something very important here. Well, if I look at it from the shut-in point of view, I can see this is the line. Things are static. Water is heavy. It will go down at the bottom of the hole. Hydrocarbon is light. It will go on the top of it. I will see a transition. So that's because water is heavy, as I said, compared to the hydrocarbon. So the water will be at the bottom. And at the top, I can see the hydrocarbon. And again, I don't care what type of hydrocarbon it is, because I'm after now identifying where the water zones are coming. Now, if I let the well now, and instead of being shut in, the well to be flowing, and I can see a rise, there is a rise here, a rise of the water level, I know that till today, the perforation at the bottom here are still producing water. Why? Because the water level in the well bore is rising. If there is no more water production and these are not producing anymore, I will not see any change in that level. There is no more water sources. Now I saw the transition here. I can see the transition. The water is coming up, increases. So this means that's a confirmation that all these perforations down here are producing water. So Mr. Customer, or whoever are holding this well, you need to shut down this perforation. How can I shut down this perforation? In this case, put a plug in here. If you put a plug in here, you isolate these. So these will not produce anymore. It will not contribute to what you have. So look at decisions that we do now. By looking at these logs, I can make very, very important decisions. And I can see this one is producing, this one is not producing, this one is producing gas, this one is producing water. What do you need to do with this type of perforations? So I can really, really do my production logging properly. So this is a flowing pass. And you can see clearly the transition, the rise of the water level. The rise of the water level means that the lower perforation are still producing water, and we need to shut this perforation. So water is rising up, and there is a flowing in there. Okay, so lower perforation is still producing water, and you need to do something about it, either to squeeze them. If it is my well, I will put a plug in here and isolate these lower perforations, and then you call it a go. In this case, there is no need to worry about it anymore. Okay. All right. So now we are in the wellbore. We identified where the gas is coming from. We identified where the water is coming from. Now, at what rate they are coming? Okay. What is the rate of these flows? So what we call the flow rate. So the flow rate is very important. Yes, we understood the flows inside our wellbore and where they are coming from, which is a very important piece of information that we actually came up with. Now, at what rate or at what flow rate that these perforations are coming, or these measurements are coming? Okay, we do this with tools called flow meters. Okay, don't tell us that you will surprise us also to see that these are very, very simple ideas. Yes, they are very simple ideas. As simple as the temperature log, as simple as the capacitor log. Flow meter is even simpler. I will take you to the flow. What is the flow rate, first of all? Flow rate, if you look at the flow rate, is actually, if you have any cylinder here that has a cross-sectional area A. What you are talking about cylinder? Because your well bore is now a cylinder. Why? Because it is the casing. Casing is cylindrical shape. Okay, very nice intact cylinder. So it is a cylinder. It's not really an open hole, which has a different caliper measurement and different diameters at every depth. No, it's a cylinder. So now have a cylinder, okay, with a cross-sectional area A. Now there's a fluid coming in with a velocity V. Now we identify the Q as V times A. V is the velocity, A is the cross-sectional area. So Q is V times A, where Q is the flow rate, V is the velocity, A is the cross-sectional area. Okay. Now, area is very well known. It's pi over 4 d squared. What is the d? Is the diameter of the casing. Okay. Some people say, well, the casing sometimes can have some scaling and stuff. Well, if you really want to go and do a caliper and to measure all that's inside of your well bore and you are that sensitive, that's okay. I'm not the kind of guy who really goes and see these very detailed things, because it's all measurement anyway. Anyway, so but actually you can actually get the area across at every depth using a certain type of caliper that you can go and measure the diameter. In our industry, the flow rate that we go, it doesn't go for centimeter cube per second or whatever. We go for as barrels. Okay, so there is a conversion factor. So say Q is a conversion factor V times A. That conversion factor takes us from the SI units into our units in our industry, which is in barrels. So the C is just a conversion factor to convert this equation into barrels per day. Okay, so it's just a unit. So here is our casing, and here is where the fluid comes in. How can one measure flow or flow rates? Okay, it's actually again simply by measuring the velocity. Oh, that's true, because C, the flow rate, Q equals V times A. Cross-sectional area is known. So all I need to do is to measure the velocity of the fluid. Okay. Flow rate and velocity are correlated. Yes, they are correlated. Radius is known, or if you want to be more accurate, go and run a caliper. Then the question now goes, I know the cross-sectional area. Now tell me how you can find, how can you measure the fluid velocity? Again, you will be surprised. It's in elementary school. Do we measure flow rate in elementary school? Yes, with a very simple idea that we learned in elementary school. Okay, what is that idea? Let me take you back to elementary school. In elementary school, actually, they told us, if you have a magnet, here is a magnet. If you have a magnet, it is north and south. There is a magnetic field lines between going from north to south. We learned this in elementary school. Now, also in the lab in elementary school, I'm not sure if they do that these days or not, but in the lab in elementary school, if you get a wire here, okay, or a piece of metal, okay, a rod, and you started moving the rod up and down, and you connected the two ends of the rod to a voltmeter. Okay, what will happen if you move this piece of rod inside the magnetic field intersecting these lines? We knew that when intersect the lines of a magnetic field, an electric current would come in. Electric current will move, so the intersection or the cutting of the magnetic field by anything, it will actually produce a certain type of voltage if you measure this voltage in a by a voltmeter. We call it EMF, electromagnetic force. I don't want to go through into the definitions of physics, but that's essentially what you do. Okay, it's the north and the south. Here are the magnetic field lines. Now you get a piece of rod, you go up and down, cutting these piece of rod, the lines here, so the current will actually move inside the wire, and you can measure the voltage. It's as simple as such. Now, what if I increase the speed of the movement? The current will increase. What if I decrease the speed of the movement? The current will decrease. So to measure the speed, try to make something that actually cuts a magnetic field line. So that's simple as this is the idea. Try to come up with something that actually moves inside a magnetic field, and let that something that you will use cuts the magnetic field lines. And it depends on the speed of what you're doing that will relate to the velocity that you have. Okay, so in this case, the phenomena is disturbing magnetic field lines with a wire. What will happen is an electric current will flow. We call this induced current. You see right there, we call it induced. It means something that's induced by this movement. So this is an induced current. So an electric current will flow as an induced current. Okay, measuring this current, high or low, will tell you if you are actually moving with a high speed or a low speed. So this will actually measure the higher the speed of the wire, the higher the voltage, and vice versa. The lower the speed of the wire, the lower the voltage. So actually going there, the speed is the way that we measure. So the speed is the velocity. So this is the idea that we will use to actually measure the flow rate. Is this the idea? Yes, this is the idea. I'll show you now how this tool actually works. So the idea of the tool is try to get the flow rate inside your well bore, move something That something needs to go and cut a magnetic field line, and that will induce certain current. The higher the current that you induce, the higher the velocity that was cutting the magnetic field. So let's design a simple flow meter. Here is the simple flow meter. Okay, what we will do here is the flow. The flow will have actually a spinner. Look at this, we call this is a spinner. We'll talk about the spinner, how the shape. Spinner is just something that can easily rotate. Spins from even the name. It spins. So when the fluid comes in here and actually hits the spinner, so the spinner will rotate. When the spinner rotates, if you look at this, here is what? Here is a magnet up here. So when the spinner rotates, it cuts the magnetic field. So it is exactly what we learned in elementary school. Exactly what we learned in elementary school. Okay. Once the fluid comes in, it rotates the spinner. The spinner goes inside the magnetic field, and the higher the velocity, higher the rotation, the higher the induced current, the lower the rotation, the lower the induced current. I can take this and calibrate it to velocity, as simple as such. Here, actually, you take this as a cross section, and here the fluid comes in here, and here are the plates. Okay, the plates of the spinner. Here the spinner, and here are the plates. The fluid comes and hits the blades, and this one rotates. This just take you a little bit more on the blades. Here's how the blades. You see that the curvature here. The fluid comes in here, and this one rotates. It hits the lower part and makes this one rotate. So it's just what you do here is just a technology thing, just a manufacturing thing. But the idea is make the fluid rotate the spinner and let the spinner rotate inside a magnet. And the more the spinner rotates, the higher the induced current, the higher the velocity. The lower the velocity, the lower the spinning, the lower the current, and that's how we translate velocity into current, and we measure the velocity in this case. Okay, so the fluid comes in, this one rotates and actually changes into electromagnetic forces. This is our rotating blades. Rotating blades rotates inside the magnet. Here is the magnet that the blades rotate inside, and the rotation inside the magnet will produce a voltage or electromagnetic force or current or whatever you call it. All of them are related. And then you can actually read this to velocity. Okay, so the higher the voltage, the higher the fluid speed, the lower the voltage, the lower the fluid speed. Okay, so that's how the flow meter actually works. Okay? You just go back to the India example. Actually I'm exceeded the hour now, I guess, but that's okay. Just give me a few minutes. Okay, so here is the Indian example. Here is the same example that we had. Did you run the flow meter? As you ran the flow meter. Here is the flow meter. Again, 4 down passes, 4 up passes. Similar, because all of these are run at the same time. So they run the temperature log, they run the capacitor, and also they ran the flow meter. Look at the flow meter here. Look at here. There is nothing changing there. Look at that. Velocity is hardly changing. This means there is no freely flow. There's no difference in higher flow rate from the bottom. It's still producing water, but not in a high flow rate. You can see here the flow, but here you can see big change in velocity. Now, when the gases are coming in, look at when the gas came in here, you can see the sudden change happened when the gas came in. Gas came in with a very high velocity, and you can see the velocity is changing, the flow rate is changing. So the flow rate here came up clearly at where the gas expands here and where the gas is coming in. So this zone shows that you really have a for up and for down, and here are the big transition change in the velocity really coincide very well where the temperature showed big flow of gas. The big flow of gas here that actually affected the flow rate and increased the velocity in this case. You know the velocity, you know the cross-sectional area, you can actually calculate the flow rate. Flow rate calculation is not as simple as I'm saying, but let's just leave it that way for that level of this course. So let's just go as Q equal V times A. There are some things that you go for the flow regime. Is it really a laminar flow? Is it a turbulent flow? I don't want to waste your time into this. It's a little bit of higher. Probably if there is a need for this, we can talk about this in another webinar. But yes, you actually look at the velocity distribution, you look at the regime that you have there. Look, it's laminar flow, it's a turbulent flow, and there are two different things there that you need to take care of. But anyways, Q equals V times A, and from this you can actually calculate the flow rate. Okay, did you do that? Yes, here we calculated the flow rate. Flow rate here is very, very low, and the flow rate becomes much different in this part. So the higher the flow rate, the highest flow rate actually came at this point, and you can see this is the flow rate of that. Okay, so this is the gas flow rate as we saw, confirmed by the temperature log. So in this well, we ran the temperature log, the capacitor, the flow meter, and we came up with a very interesting understanding where the water is coming from, where the gas is coming from, at what flow rate that this wellbore is produced. Okay, so thank you very much for your listening to this webinar. This is the end of part 1. Until we meet, guys, in part 2, and I will be very happy to answer some of the questions. Mana, if there is any questions.
Thank you so much, Dr. Moustafa, for this informative webinar. You will answer the question this session?
Yeah, just 1 or 2 questions, and then if there are some other questions, we can actually cover them in the next one.
Okay. First question, is it temperature drop due to gas only encased holes?
Yes, the big drop is in gas only. Actually, as I said, if it is 1 or 2 degrees, don't make a big decision on this. 1 or 2 degrees, oil also can drop the temperature a little bit. Water will not. Water will increase the temperature. Okay, but oil can do this a little bit. Can actually drop the temperature. But as I said, to actually make a good decision with a straight eye and say yes, this is gas. Okay, look for 3, 4, 5, 10, and so on. So make the temperature drop considerably. Okay, don't go for 1 or 2. Go for 4, 5. That would be good. 1 or 2 to be a question mark in there. So don't rely on a small drop of temperature. Make sure that the drop of temperature is good enough that you can make a good decision without any hesitation that this is a gas zone.
Okay, and the second question, why do we keep the air dielectric constant alongside the materials constant in the equation?
Because the epsilon r is not a value, it's a ratio. The epsilon r of the dielectric constant is the ratio between the material versus air. So the epsilon r is epsilon material divided by epsilon naught. That's the definition. Okay, it's really a very good question because I didn't know that people actually understand that. That's why I just left it that way. Epsilon r is the ratio between the dielectric constant of the material divided by the electric constant of the air. So epsilon r equals epsilon material divided by epsilon naught. Now, if you multiply epsilon naught, epsilon r, then epsilon naught will cancel out and you will end up the material. So epsilon naught, epsilon r multiplication give you the dielectric of the material because epsilon r is epsilon material divided by epsilon naught. I hope this is clear, but probably next time I'll make a slide to show that because it's a very good question.
Okay, can we take just one question?
Yeah, go ahead.
Another question. Is there any tool to detect solid deposits in casing?
Say it again.
Is there any tool to detect solid deposits in casing?
Solid deposits. Yes, there is.
Yeah.
There is a way. There is a way of do this, but that goes for the casing inspection. That's not for. See, in this webinar, we said we will talk about what's inside the wellbore. What's inside the wellbore are the fluids. So in this part, yes, we are now concerned about fluids and flow rates and what type of fluid is there. His question relates to the casing itself, which we will cover in the next webinar, hopefully. I can cover the whole thing between the casing and the cement. Yes, we do that. We have tools that does this, but that's not what this webinar that today. but that will be covered hopefully by on next Thursday.
Okay, thank you, Dr. Moustafa, again.
Thank you.
And to all attendees, Dr. Moustafa will continue answering all your questions next webinar. And to highlight, this session has been recorded and will be uploaded soon on PyPatro YouTube channel, so make sure to subscribe in our channel. Thank you all, stay safe, and bye.
Thank you very much. Bye-bye.